Hi everyone, and welcome to our lecture on developing the torque speed characteristic for the induction machine. By the end of this session, you should be able to develop the torque speed characteristic for the machine, identify from that characteristic which is the large slip and which is the small slip areas, derive the large and small slip approximations, and derive the equations for maximum torque and the slip at which maximum torque occurs. So we're going to do this, we're going to make use of a simplified equivalent circuit, and it is simplified only in the sense that I have summed X equivalent and R equivalent into single values, and I have here the electrical side and the mechanical side of the machine. If you remember from your power flow lecture, the power flow in the induction machine. So you can no longer clearly see where the air gap is because these parameters are both rotor and stator included, but the same current goes through them, so it is not simplified in terms of making any further approximation. You just have less parameters to deal with. So I want to derive the torque as a function of the speed, or the slip in this case. So I know the developed torque is equal to the developed power over omega. Now I have the developed power, which is the power that goes into the mechanical system here, which is I2 squared multiplied by R2 on S multiplied by 1 minus S. I squared R, that is the power in this resistor, multiplied by 3 for the 3 phases, divided by omega gives me the torque. So in order to find now what that torque would be in terms of these parameters, I have to see what I2 is. So I could find I2 if I know V, which is what I actually input into the machine. Remember, I don't input I to the machine, I connect a voltage source to it. So I input V, and the magnitude of the current that goes into the machine is equal to, remember this V here is the same V that is across here, so this branch will not cause any problems for us in the calculation, divided by the magnitude of this impedance. So the magnitude of this impedance is, remember this R equivalent is R1 plus R2 over, sorry, R1 plus R2. So I have R1 plus R2 prime is my R equivalent. When I add that to this, I get R1 plus R2 prime on S. So square root of resistance squared plus reactance squared gives me the magnitude of my impedance. So the magnitude of the current is the magnitude of the voltage over the magnitude of the impedance, and I could take this entire thing now and substitute it into here for I2. And when I do that, I will end up with this equation. So in this equation, I have my developed torque, my slip, all these parameters are fixed, V, R, and X. The things that vary would be omega and the slip. Now, this omega here is the mechanical speed, but I could substitute this for the or I could use the relationship that I know, which is omega is equal to omega S multiplied by 1 minus S, to represent this speed in terms of a constant value, which is the synchronous speed, and the slip. And if I do that, so if I simply replace this with omega S multiplied by 1 minus S, you'll see this will cancel with that, and what I would get is this equation. So here I have the developed torque in terms of the voltage, a set of parameters of the machine, the frequency, all these are constants, and the only variable is the slip. So I could now draw my characteristic for torque versus slip. So if I plot this for a given voltage and given R1, R2, and X equivalent, I will see that I could plot it torque versus slip, and this is the sort of shape I will get. This is just a sketch. So you'll see one of the interesting things here is that it goes from 0 on the right hand side to 1 on the left hand side. That is because 0 slip is the max. This will be omega s, and this will be 0. So this is 0 speed, synchronous speed. At synchronous speed, the slip is 0. At 0 speed, the slip is 1. So you'll see that it's not a nice linear graph the way we got in DC machines. We have this non-linear curve here. So what we could do from here is we could identify certain regions. So the first region is from S max going to 0 from the slip at S max this way. We call this a small slip region, because in this region the slip is very small. It is close to 0. And then on the other side here we have the large slip region. So we are going to simplify this equation for these two regions so that it can make it easier for us to calculate some other variables of interest. So now let's look at the large slip approximation, and that is this area that we are looking at here. And the first thing we could say, if we go back to our equation, is what happens when the slip is large. Let's look at this value here. When S approaches, remember S varies between 0 and 1. So this value will get larger as S becomes smaller. For the large slip approximation, S is becoming larger, so this value here is becoming smaller. And in fact, what we would find happening is that this on the whole will become small when compared to the reactance. Remember, the larger slips, the frequency is larger, which means the value of X of this reactance is getting larger as well. So we have this value getting smaller and this value getting larger when we have larger slip. So since we have this relation, we could just forget about these and we could simplify it to this equation here, where we just consider all of this negligible, and we get 3v squared r2 prime on s omega s x equivalent squared. Now one of the things we could do with this is we could look at the position when the slip is 1, which is when the speed is 0. So when the slip is 1, I just set this equal to 1, and I end up with this, which is my torque at 0 speed, which is my starting torque. So if you want to start something, if you want to move something, and these are often the times you have you need additional force because you have static friction to overcome and so on. To do that, you sometimes need to meet particular requirements for your starting torque. So we could calculate it very simply with this equation here. That is what we get out of the large slip approximation. Moving to the small slip approximation, we have, in this case, as S becomes very small, this value becomes very large. And since this value becomes large, we could get rid of this, and we could get rid of this, and then these will cancel here. Of course, this one is a squared, so you'll still get 1 on the denominator, and you end up with this equation here for the small slip. So that one, we don't have anything like starting torque or anything to consider, so it is just a simplified equation that you could use once you're on this part of the characteristic, which is the operating, the full load side. This is where you'd usually be when the machine is in operation at rated values. Now, maximum torque. We have this curve. We need to find what is this value here. So as per usual, what we need to do is we need to differentiate and find what that turning point is with respect to the slip. And when we do that, if we differentiate this equation here with respect to slip, you could use your quotient rule or your product rule if you want to take the denominator and bring it to the numerator. with a -1 index. When you do that, you get T max. Of course, you do that, set it equal to 0. You get T max is equal to 3v squared on 2 omega s r1 plus square root of r1 squared plus x equivalent squared. And that happens at a maximum, at a slip of r2 prime on square root of r1 squared plus x equivalent squared. So remember, this S max is not the maximum slip. The maximum slip will always be 1 when the motor is off. This S max is the slip at maximum torque. Right? This is the slip at maximum torque, not the maximum slip for the machine. So to summarize what we just covered, we developed the torque speed characteristic from the induction machine, and we did this straight from the equivalent circuit using I squared R with our mechanical, the resistor that represents the mechanical power, divided by the speed, and we get our torque. We identified the large and the small slip areas, and then we use the slip in our equation and looked at it as it tended to 0 and then as it tended to 1, and we derived the large and small slip approximations, and we also derived the equations for maximum torque and the slip at maximum torque.